Hello and welcome. Today, we're diving into a critical issue affecting our planet's largest ecosystem, the oceans. You've heard about carbon dioxide emissions warming the atmosphere, but did you know a significant portion of that CO2 is absorbed by the sea? This absorption is changing the very chemistry of seawater, a process called ocean acidification. It's making the water more acidic, lowering its pH, and threatening marine life from corals to shellfish, and ultimately, the billions of people who rely on healthy oceans. Understanding how quickly and severely this is happening is vital. That's where monitoring comes in. Scientists use a combination of tools. Traditional ship surveys collect water samples for detailed lab analysis. Moored buoys and fixed stations provide continuous data from specific spots, like watching a pulse point. To cover more ground, autonomous platforms like ocean gliders and floats roam the seas, collecting data across vast areas and depths. Sensor technology is also rapidly advancing, with smaller, more efficient devices measuring pH and other key factors directly in the water. Even satellites and complex computer models help paint a bigger picture of ocean conditions. But monitoring just tells us the problem. What about solutions? Beyond the essential goal of cutting global CO2 emissions, researchers are exploring engineering approaches to directly counteract acidification or remove CO2. One major area is ocean alkalinity enhancement, or OAE. This involves adding alkaline substances, like finely ground minerals, to seawater to neutralize the acid and help the ocean lock away more CO2, potentially for thousands of years. Another OAE method uses electricity to make seawater more alkaline. Then there's direct ocean capture, aiming to pull dissolved CO2 straight out of the seawater, somewhat like capturing it from the air. Biological approaches are also being studied, such as large-scale seaweed farming, where the seaweed absorbs CO2 as it grows. The idea is then to sink the seaweed, or use it in long-lasting products. Finally, restoring coastal blue carbon ecosystems like mangroves and seagrass beds helps them naturally soak up more carbon. It's important to stress that these engineering ideas are mostly still in the research phase. They face big hurdles. Are they scalable? What's the cost? How much energy do they need? And crucially, what are the potential side effects on marine ecosystems? We need much more research, small-scale testing, and careful evaluation before any large-scale deployment. These techniques aren't a substitute for cutting our carbon emissions drastically, which remains the most critical action. But they represent potential future tools in our toolkit to help protect our vital oceans from the ongoing threat of acidification. Thanks for tuning in.